by 1.963 times 10 to the power minus 3 times by 101 times, oh, sorry. Then you multiply by 101 times 10 to the power 9. So that's the first one. Plus, again, minus by P2, because everything is under what? Compression, 0.5, divide by 314.159 times 10 to the power minus 6, and it's made of steel, times 10 to the power 9, and then the last one plus, and the term is exactly the same. I only need to come over here. I just need to change this to P3, and we're good to go. Okay, P3, right? Okay, so note that P1 is going to be equal to P2, right? It's going to be P3 is equal to PR. Does that make sense? Yes or no? Right? Because BC is going to fill PR. AB is also going to fill what? PR. And then finally, DA, all of them are going to fill what? PR. So it makes sense, right? Where P1, the load applied at section 1, P2 is the load applied at section 2, P3 is the load applied at section 3. All of them will be felt, and the magnitude is going to be what? Equal to PR. So when you substitute everything in, all right, so the deflection due to the redundant load. Oh, sorry. Any questions so far? Anyone, please? No? Give me a few more minutes, okay? Then we go for our first break, okay? Or our only break. So we have deflection due to the redundant load will be equal to minus 1.261 times 10 to the power minus 9 PR plus, oh, let's forget about plus, everything is minus because everything will go into compression. So 7.9577 times 10 to the power minus 9 PR, and then same thing, minus 1.261 times 10 to the power minus 9 PR. Okay, so the redundant load is going to induce a minus 10.4797 times 10 to the power minus 9 PR. Okay, so finally we're going to apply the deflection due to the load plus by the deflection due to the redundant load. Oh, sorry, the deflection due to the load plus by deflection due to the redundant load must all equal to what? 0. So due to the load is 1.655 or 1.655 times 10 to the power minus 3 plus, right, minus what? 10.4797 times 10 to the power minus 9. Okay, PR, the whole thing is equal to 0. Remember what I told you guys. The deflection due to the load and the deflection due to the redundant load, the magnitude, okay, it's a vector, is going to be opposite, yes or no? If the load is going to be tensile or going to be tensile, the redundant will be equal to what? Compression. Yeah, there you go, right? You all saw that now, right? You all physically see that now, okay? So from here, you can calculate PR. Okay, so PR will be equal to 1.655 times 10 to the power minus 3 divide by 10.4797 times 10 to the power minus 9. So this will be equal to 1.655 power minus 3 by 10.4796 power minus 9. So it's equal to 157 okay, 0.924, right, times 10 to the power 3 Newton. Okay. Now, which direction is this acting at? Okay, so the direction it's acting at is going to be towards the left-hand side. Why towards the left-hand side? Towards the left, because PR over here is towards the left. Okay, so it's positive, we follow that direction. So when that's the case, this is also equal to our what? This is also equal to our CX. Okay, so our CX is pushing towards the what? Towards the left-hand side. Okay, so from here, once you know that CX is going to push towards the left-hand side, so what we do now is we go back to our free body diagram, right? We have assumed wrongly. We did not know, okay? I did not know also. So we cancel this, right? We not cancel in the sense, we change the direction, okay? And we change the direction, you change it this way. It's going into compression. Then the next thing we're going to do, so let's check whether it's our answer correct, right? So it's equal to what we have is 107. So here you go. Okay. I think they have it opposite. $157. Oh, sorry, they got it correct. So they are 157. Okay, maybe I wrote wrongly. Yeah, 157. So this is our CX. Okay, our CX is 157. So there you go. So it's correct. So the next thing that we do, we're going to apply CX. All right, we have formed this equation. So we're going to apply equation number 1. Did we call it equation number 1? Yeah, we're going to apply equation number 1. So CX, right? CX. So I'm going to write down apply equation number 1. Where we have CX minus by DX is equal to minus 50 times 10 to the power 3, right? So when we form this equation, CX is going towards the what? Right-hand side, yes or no, right? So for this case, we know that CX is going towards the left-hand side. So we are going to put in minus 157.924 times 10 to the power 3 minus by dx is equal to minus 50 times 10 to the power 3. So we get dx will be equal, so we bring over, so will be equal to minus 107.924 times 10 to the power 3, right? Newton. So we realize that, hey, we also got it wrong also, because when minus means the direction is wrong. So this will be equal to 107.924 times 10 to the power 3 Newton, and is going towards the right-hand side.
Right.
Yep, right. So we go back up here. We did not know. Initially, we do the man pushing upwards is a good assumption, but it can be corrected. So this will be going this way now. Okay. So now we have calculated the forces, and then if we were to draw the free body diagram, or we draw the actual loading condition. Okay, so I'm give me like 1 more minute. Okay, so if we were to draw the loading condition now, right? So this is one part. This is our second part. So what we have now is we have a load coming in this way. This is at 107.924 times 10 to the power 3 Newton. So this is your point D, point A, and over here you have a load going at 150 times 10 to the power 3. And then you have 200 times 10 to the power 3. So this is your point B, and this is your point C. You have a load coming in at 157.924 times 10 to the power 3 Newton. Okay, right. Go for a break. Come back at 8:15 and we start again. Thank you.